you've had a chance to look at the Canvas and review the syllabus or glance through it at least. How many of you have done that? Just a short show of hands. Okay, good, great. So just in a nutshell, going over the basics, sort of the overview of the course, which has been laid out in the syllabus. This is a 10-week course, obviously. The basic requirements are stated as statics, dynamics, and strengths of materials. Also, if you look at the syllabus, there are other important information there. I have 2 sets of videos of prior lectures when I was teaching the course that they're now on YouTube. And nothing has changed since then. Mechanical vibrations hasn't changed, although I have to say that each time you teach a course, you kind of tweak and introduce some more interesting stuff, which I always do. But nevertheless, if you want, you can just watch those videos and as a good resource. The only thing that has changed is I was just a little bit younger, and so were you, right? But other than that, I also will place the video lectures for this course, including all the notes, which are already on Canvas. I will place the lectures that are recorded now also on Canvas and eventually on YouTube, so you have easy access to those. And what else do you want to know about the course before we actually start? There are typically 2 exams, midterm exams, and I normally also have 2 team projects. One of them I call the mini project, which is kind of conceptual, and the second project has always been you build something, having learned that demonstrates your understanding of all the fundamental concepts you've learned in this course. It's been a really fun part of the course. Unfortunately, due to COVID, since last year, I had to stop that. So I would not be assigning that project number 2 because it requires access to the shops and building something, and it's not easy. So we'll have 1 project, 2 exams, and a final exam. All these assignments are take home. I always encourage, and also 4 sets of homework. These are, homework sets that help you sort of understand the materials in the course better. I always encourage teamwork and collaboration in everything you do, including the project and homework. It is only the exams that, although they are take home, I do strongly expect and encourage you do that independently. But you can always exchange, of course, ideas, even if in the exams you want to discuss some general concept, for instance. Okay, how do you find, or what was the best approach to solve the Duhamel integral? Somebody may have a better way of, describing it for others. So in general, I do encourage collaborative work because that's what I believe you learn best. And also you're at this stage of your education, being a junior, that, you know by now that, that you have responsibilities and in sort of learning the concept and the courses because you want to be good at it. So with that introduction, I guess, and also talking about the course, the textbook, I do not expect that you purchase any textbook because the textbook that I have suggested in the syllabus, Mechanical Vibrations by Rao, 6th edition or 5th edition, is available for free. A PDF copy is available. You can download that. And that's a reference book I use. And as I said, all the notes I do put it on Canvas. So you have access, full access to that. Okay. So any questions, any general questions before we start? No? If not, so let me switch from this video mode to my sort of writing board, which is this, okay? And we will start. So let me, again, remind you, or at least inform some of you may not remember what the name of this course was. This course is Mechanical Vibrations, which is also referred to as the structural dynamics. Both are the same concept applied to two different types of structures, mechanical or structural. And today is 29th of March, the first lecture. All right, so this is what I usually do in the first lecture. Just give you sort of a very broad background, sort of laying the ground for what is coming. So with that said, so first let me sort of give you a sort of a overall perspective of what mechanical vibration as a course is within the context or within the chronological order of the courses that you have taken or will be taking in engineering mechanics. So mechanical vibration is a field or a topic within the field of engineering mechanics. So what was engineering mechanics, or what is engineering mechanics? You've taken a few courses in engineering mechanics, so by now you know what it is about. Engineering mechanics is basically the study, or is basically a science that gives you an understanding or provides you the tools and the understanding of the action of forces on a body. Instead of philosophical, I mean, expressing it in a philosophical way, that way. In other words, what happens if an object, whether it's a structure, a human body, a planet, doesn't matter, any object that you can think about, imagine, that exists in the universe or multiverse, right, exists, is acted upon by other objects, is in contact with other objects. This contact generates what we call a phenomenon called force. And we are always interested to know when a force acts on an object, on a body, what happens to that object. So in order to understand that, chronologically speaking, the science evolved. The evolution of this engineering mechanics reflects also how we started understanding the action of a force on objects. The first sort of the fundamental course in engineering mechanics is what you had, statics. In statics, due to lack of the knowledge, in part, at the time this field was developed, or making simplifications so that we can better understand or be prepared for understanding how to deal with more complex objects, we made two assumptions. What the assumption was, the most important assumption was, as far as the objects are concerned, and objects, as I said, are, which also are referred to as bodies, means anything that you can imagine exists in nature. Okay? A structure, a light pole, your body, planet Earth, a tree, anything. So in statics, we assume that objects are rigid. What does that mean? That means under the action of forces that obviously develop due to the contact of this object with another object, these objects cannot change their shape. They're rigid. So that was one fundamental assumption that we made about the bodies. And the second fundamental assumption was that the forces that act on these objects are not time dependent. They're constant. So they're time independent. Now, what did we study in statics? The objective was to understand when a force acts on this object, what happens to that object? What kind of internal forces develop in an object? That was it. Then the next sort of, in a way, evolutionary or evolution in understanding the behavior of objects under the action of forces was, how about if you still assume the object is rigid, but the forces that act on the object are time dependent? Okay? So that's what dynamics was all about. So the systems that we studied were the same. In general, they were rigid, no deformation, but the force acted upon these objects was time dependent. So for that reason, then what we were interested in terms of the actions that these forces do to these objects were a little bit more than just finding these internal forces, but also, for instance, as the object moves, how do we find the velocity, the acceleration, or understand in a way the behavior or the motion, understand better the motion of these objects, okay? But in both of these, still we make this critical and wrong or simple assumption until you took the next course in engineering mechanics, which was the mechanics of deformable bodies. Of course, you didn't call it that way. This course is typically called the strengths of material or the stress analysis. So what was the biggest jump from these two courses to this subject? That we broke away from the assumption that the bodies are rigid. Bodies were flexible. Okay? So what was the big deal about that change? Although though, we still assume that the forces were time independent or constant, right? So in this course, we look at the effect or the impact of forces on objects that are flexible. That means that we now were able to get more into in-depth understanding of the action of the force on an object. That an object and the force is not just generates a force, is not just causes some motion, but also deforms the body. How does that deformation happen? Because internally, these forces cause something or internal forces that the intensity of those forces are important. And the intensity of the deformation that these forces cause are important. And those intensities, we call them the stresses and the strains. Why are those important? Because any material that you can think of in the world, whether it's steel or rubber or whatever, their intensity of their tolerance to the loads that are applied to them is limited. We call that, for instance, ultimate stress or ultimate strain. So we introduce these topics to understand if you want to design a structure or design a mechanical system, what is the criteria that we need to follow? In order to design an object, the criteria that we need to follow is that the maximum stress that these objects are subjected to should not exceed the maximum stress that that material can handle. So understanding basically this topic helped us better design a system. So this is all that you have studied in engineering mechanics, except that when we are talking about bodies, bodies do not necessarily mean a body that has a confined or sort of space that it occupies and its volume is fixed and is predefined. A body can change its shape depending on the space that it or the volume that it occupies. Or in other words, that body can be fluid. So fluid mechanics is also part of this engineering mechanics that we studied, and you study the dynamics of fluids or fluid dynamics or statics. Fluid is statics, action of static forces on fluids. But nevertheless, that was it. So now what do we do in mechanical vibrations? In mechanical vibrations is a combination of all of these, or in other words, we go to the next level. That is, we want to see if we have a flexible body that is subjected to a general type of loading, time-dependent load, which can be of different forms and shapes. How do we design this system to withstand that load? Or the ultimate goal is to find dynamic stresses and strains that develop in an object, which is those quantities that determine, or we need to abide by those in order to design an object. Give you an idea. You want to design the wing of an airplane. Wing of an airplane is subjected to an external load that is caused due to jet engine, right? Is a cyclic motion, okay, with high intent, frequency. Now, how do you design that? You need to know when this forcing function is acting on that wing, what are the dynamic stresses that develop? So it is not just that we find how much that wing is displaced or how much force is generated in that, but also the time-dependent stresses and strains. So that's the ultimate goal. So let's, in other words, if I can, in a better way, sort of help you to visualize and understand what you have studied in engineering mechanics or you will study in mechanical vibration, the best way of describing the objectives is this. Engineering mechanics, no matter what topics or what field, can be best described, in fact, by a system diagram that consists of three components. You do have an input. You do consider any structure in the world. It is subjected to an input. This input in engineering mechanics is typically a force. And in general, this force is time dependent. This force acts on what we call a system. System is the broader and a more general description of a structure or an object or a particle or whatever you've had so far. But system is something that we need to in other words, represents a real structure or is a model of a real structure. Due to the action of this external input on the system behaves or reacts to this input and responds to that. So the ultimate goal is to find out what is this reaction or what is the response. So let me give you an idea. In the statics, the system that you had was a rigid body or maybe a structure like a truss or a frame. You consider these forces. The ultimate goal was you wanted to know what these forces do to this structure internally. How do you find the internal forces in a truss? In mechanics of materials, the system was a representation of a structure, like a beam or a shaft or a plate. And you want to know when you have a force acting on a beam, how that beam deforms. So in that course, the ultimate goal was how to find deformation, how to find the stresses and the strains in a beam, in a shaft, and so on. In mechanical vibrations, the system is a deformable body like a strength of material. The force is a time-dependent force. The response that we are looking at are displacements, the stresses, and the strains. And the only difference between this type of response and the responses that you encountered in a strength of material was all of these are time dependent. And ultimately, we are interested in the maximum value of these quantities because that is what we design a system for, to withstand that maximum value. If you have a cyclic motion, a jet engine acting on a plane, on a wing of an airplane, you want to know what is the maximum stress that can be developed. So given the material that that wing is made of, to design a wing or structure that can withstand that force. So that's basically what we call a schematic description of engineering mechanics. Input, system. System is something that we will deal with it very thoroughly. System is the representation of the real world. I'll get to that in the next lecture, what we mean by system. In mechanical vibrations, we do, remember in statics, we first studied forces, how to deal with forces, how to represent forces vectorially, how forces add up, how forces rotate an object. Once we understood forces quite well, then we looked at the effect of forces on rigid bodies. What kind of internal forces these external forces cause in an object like a frame, how you find forces at the joints. In mechanical vibrations, we will need to understand what these forces are. So we will tell you what kind of forces we will be dealing with. In statics, it was easy, constant forces. In dynamics, it was relatively easy. In mechanics of materials, constant forces. Here, forces are not just one type of force. We will need to know what kind of forces we're dealing with. As far as the system, we need to describe the system. In a strength of material, systems were modeled by some simple models. We call them beams, bars, shafts. That's it. That's all you dealt with in strength of material. These systems represented the behavior that a real structure may experience under the action of forces. And they helped us to understand what happens to that real structure. In other words, we defined then the stresses and strains. That's exactly what we will do in vibration. So, but for that, for the time being, let's suffice to that. We will really start mechanical vibration next time. What I like to do today is just briefly go over some background knowledge that you have, in fact, accumulated so far, which you need to refresh and helps you with dealing with the topic of mechanical vibration. And these are basically the mathematical tools. And there are two of them. How to solve differential equations. We use two, basically, a tool to deal with differential equations, and also another tool which we will, I will go over that, which is complex algebra. But before I even refresh you on these sort of background mathematics that you need, I always like, and honestly, in a way, enjoy to give you sort of some historical perspectives about this subject that we are going to study. And what is that historical perspective? The appreciation for those giants, those scientists who we should really be sort of appreciative of and acknowledge them for helping us to be where we are, to be as, basically humanity or society, the world. So when it comes to science and engineering, who were those who really introduced for the first time, discovered the understanding of the concept of mechanics, motion, especially that unfortunately in your typical high school studies, they don't really give you an appreciation of these people, these individuals, so that you develop a little bit of modesty and humility, that all these we learn is nothing compared to what those giants introduced for the first time. So going back, I always like to talk about these individuals because they're the ones who really laid the foundation for understanding mechanical vibration. There are many people, but these are really the most important, sort of the iconic figures in the history of science and mathematics that we should get to know. The first individual is, you probably have a hard time pronouncing that name, Khwarazmi. Is a Persian mathematician and philosopher who was born in 850. Okay. He was a giant mathematician. He discovered that for every phenomenon, there's a mathematical interpretation, or you can develop a mathematical interpretation for everything you observe in nature. Really laid out the most fundamental framework for formulating the understanding of behavior, of mechanical behavior in mathematical terms. In fact, it is after his name, because in Arabic, he's called Al-Khwarizmi. The word algorithm is after Khwarizmi because he's the one who developed the whole concept of what we call algorithm. So that's the first giant who really laid out a fundamental foundation that anything and everything you observe in nature can be interpreted by mathematical sciences as far back as 850. Then comes the next giant who really formulated or developed the tools and the formulation that laid out understanding or development of what later on we call that a calculus. And his name, he is mostly known in the Western world because of his contribution of famous poetry. His name was Omar Khayyam. Omar Khayyam was born in 1048. He is the one who basically discovered the science that we know as algebra. In fact, algebra is the word he used to describe that branch of mathematics. And what was the reason? Because he was an atheist. He believed in the fact that everything that in nature is due to basically a reason that human beings cannot describe or explain, so they basically assume that they have been created. So he believed in that. So, and that sort of the mentality or philosophy is called Jabr. So algebra is this mathematical tool he developed, and he called that. Not only that, he also developed, he solved for the first time, provided the solution for the nth polynomial, which later on, and unfortunately, is called binomial of Newton. He discovered, in fact, the nth polynomial solution, laid out the word. He was an amazing guy. Then he also was an astronomer. He discovered for the first time and, in fact, created the first solar calendar, which as of today, if you go and read about it, is the most accurate calendar in the world. And that's a solar calendar. Go on Wikipedia, go on Persian solar calendar, which is the oldest laid out by Omar Khayyam, because he knew he was the first who discovered that, in fact, it is the Earth that rotates around the sun, not the other way around. So Moon was just a planet that itself is rotating about the Earth. So the whole foundation of lunar year just put to death by Omar Khayyam, because he discovered and created the solar calendar. So that's why, you should really get excited when you read about these scientists. So the next one is who really deserves all the credits for the creation of the field of engineering mechanics that we know of today is Galileo. Galileo was born in 1564, 100 years before the most famous thief in the history of mechanics, who is called Newton, Isaac Newton. Newton stole everything that Galileo had already discovered: the law of gravity, celestial motion, the uh, all those laws of mechanics. So, unfortunately, when he laid out and formulated or extended the formulation of Omar Khayyam to fully describe the whole field of motion, mechanical motion, including rigid body dynamics, it was at the time that they arrested him, almost was executed. So he could not publish any of those works. And it was not until mid 1600s that Newton came along, stole everything that Galileo had discovered already, and published under his own name. As unfortunately and regretfully, we refer to everything we know in mechanics now as Newtonian mechanics, which should be Galilean mechanics. But anyway, but there are two giants after that, actually. But it's interesting that Newton was in a way so stupid that although he assumed, or he claimed that he had discovered everything about the motion and planetary motion and mechanics and whatnot, he did not know anything about, honestly, astronomy. He said that there are these planets that are moving around in heavens. He had no idea that there was such a thing as universe, galaxies. It was not until Euler, who was born in 1707, and later Laplace, 1749, the two giants of mathematics and physics that really discovered what we know and laid out the foundation for what we know about engineering mechanics. And these are the ones who should be, especially Euler, who's the most iconic figure in the world of mathematics, because his discoveries and contributions, of course, are not just limited to mathematics, physics, science, and so on, and Laplace either. The reason I mention these, to be honest, is just, as I said, it's kind of fun, gives you at least some appreciation of the context of what we're going to introduce. And as I said, sort of gives you sort of the humanitarian aspects to the science that we're going to study. So with that said, I promise that I'm going to sort of go over some background materials that you need to get prepared for this course. As far as these background materials, I said was how to solve a differential equation first. That's the first thing we need to refresh. The good news is, although I would just quickly go over this, but I don't expect you to really go back and relearn everything you learned in differential equations. Because first of all, the differential equations we will be dealing with in mechanical vibration are very simple and very special class. We will only deal with second order linear homogeneous equations. And even with that, I don't expect you to go and remember how you solve those. We will learn them just in time. As we need them, I will introduce, basically refresh your memories on how that was. There is, of course, another way, more powerful way to solve differential equations that I am not going to talk about that, but it is important at least to sort of remind you of. Some of you may be interested in that, and is Laplace transform. That's one of the contributions of Mr. Laplace, whom I said, one of the giants in mathematics and science. What was the contribution of Laplace? He discovered that instead of solving a differential equations, or for that matter, finding the original function of a derivative, in other words, finding the original function by using an operator, which we call integration, which is not in general, not an easy thing to do, especially when you have very complicated or complex functions. He said he discovered a better way. One of his discoveries, he also did many other things like, probability and so on. He introduced an operator called, or Laplace transform. When you apply this operator, which is this, to any function, okay, you can basically transfer from the world of derivative by mapping this world to another map, which we call the S domain, okay, through this transformation. And then you do all kinds of manipulation, and by inverse of this transformation, you find the function that you were looking for. This is called, in a nutshell, Laplace transform. We are not going to, as powerful as this approach is, and as general as this approach is, I know for a fact that, having learned from experience, that you do not like this approach. So we will suffice our approach to the traditional way of doing differential equations. But the second sort of concept or topic that we need to review is complex algebra. Okay. Why? Because we will be dealing with behaviors or phenomenon that can be only explained by understanding the calculus of complex variables, complex algebra. Okay. So again, the story, what is the story behind complex algebra, right? It goes back to Mr. Euler, another giant, right? Up until the 17th century or 16th century, mathematicians were not able to solve this problem. They knew how to solve any binomial equation, but when you get to that, they would say this has no solution. It was not until Euler introduced this number referred to as imaginary number that basically opened the world for better understanding of numbers. He said that every number in the world has two dimensions, a real dimension and imaginary dimension. So if you consider any number, call that Z, it has two dimensions, X and Y, okay? X is the real part and Y is the imaginary part. So even a number like 3, so in other words, every number is a sum, this vectorial sum of its two real and imaginary components, including any real number, can be written like this, as a zero imaginary component. This may sound like a small discovery or sort of invention, whatever you might want to call that. By introducing the concept of numbers in this form, that is, any number should be represented as such with two dimensions, he opened the door for extending the basically calculus into a completely different arena, which helped us now be able to understand mechanical vibrations. So any number can be written this way. But also, if you want to represent a number, a complex number, using polar coordinate, let's say the distance from the origin is r, you realize that, okay, and the angle is theta, you realize that the real and imaginary part are related, can be converted to this polar coordinate. So this polar coordinate representation of real number would be what? X is r cosine theta and y is r sine theta. So this number that we introduced this way can be written as r times cosine theta plus I sine theta. So a number can be now written in this form, where r obviously is the square root of the sum of the squares of the two components. With this introduction, okay, he introduced also the principal operations of these numbers, meaning summation, subtraction, multiplication, and division. We don't go through the details of that, but just give you an idea, just refresh your memories as far as what you've had. If you have, for instance, two complex numbers, you want to multiply them by introducing this formulation, instead of doing it through this way, through this form, which is cumbersome, by benefiting from trig identities, if you multiply these two numbers, which would be r1, r2 times cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2, benefiting from trig identities, you see that you can write this as r1, r2 times cosine of the sum of the two angles plus I times sine of the cumulative sine angles, okay? And if you generalize this, in other words, if you have, for instance, the same number that you multiplied at n times, or z to the power of n, can be shown then that is nothing but r to the n cosine of n theta plus I sine of n theta, which is a very important, very powerful formulation. Another thing, that happened, or Mr. Euler discovered, which was very important. In fact, that is what we will be mostly used in mechanical vibrations or understanding, for better understanding of motion, was this. He was sitting one day and playing around, as he always, made his discoveries when he was having fun, playing with his grandchildren, and he was writing stuff. He looked at this. He looked at the expansion of cosine and expansion of sine, okay? We know Taylor series expansion for these two functions are like this, right? Minus theta to the 6 factorial, and so on. And this is theta minus theta to the 3 factorial, plus theta to the 5 factorial, minus theta to the 7 factorial, and so on, okay? It is based on these expansions. You remember, if you have a small number, since the power of a small value is almost 0, approximate value of cosine when the angle is small is 1, and approximate value of the sine when the number is small is the angle itself. But what Euler did, he also looked at the expansion of the e to the power theta, and he realized this. He said, if I expand this, I get this, right? Theta 2 over 2 factorial plus theta 3 over 3 factorial plus theta 4 over 4 factorial, and so on. He said, wait a minute. How about if I substitute for theta, replace that with I theta, the expansion of e to the I theta becomes something like this: 1 minus theta squared over 2 theta plus theta 4 over 4 theta minus theta 6, 6 theta plus I times theta over 1 factorial minus theta over 3 factorial, and so on. In other words, e to the I theta is cosine of theta plus I sine theta, or the expansion of e to the I theta is as if you have the cosine, instead of cosine of I theta, you have cosine of theta added plus I times sine theta, because this part, as you can see, is cosine theta. This rest is sine theta that has been multiplied by I. This was a huge discovery, because he said now a complex number can be written in its third form. This was the first, this was the third, the second, and this is r times e to the I theta. These are the two important forms that we will be using in dealing with complex numbers when it comes to studying mechanical vibrations. I don't mean to have scared you. I promise you, I'm not going to expect you to remember all of these. We will only introduce them step by step and as we need them. I just wanted to sort of give you at least a sort of a hint that in mechanical vibrations, we will be refreshing our memories about two important mathematical subjects that we have studied. One is differential equations, and second, complex numbers, but not the whole spectrum of what you studied, just part of what you studied in those courses. With that said, I'm going to stop here and see if you have any questions